निर्माण नो अभिगम कल्याण हो छात्र नो हरदम उच्च अभ्यास नो शिक्षण धाम महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल महर्षि गुरुकुल.
In this session, we will be studying regarding chapter 12, areas related to circle. Chapter number 12 from NCERT, under which we will be today in this session going on the introduction of exercise 12.2, that is area of sector and segment of a circle. First, let us move on to the sector part. What is a sector? How is sector formed? Let us go through it. Suppose this is a circle with center O. Sector is the region enclosed between two radius of a circle. Suppose we take this one as a first radius, and suppose this one is our second radius of the same circle. And the area enclosed between the two radius and the arc of the circle, or you can say the circumference part of the circle, only that area between the two radius, this region is called the center of a circle. This part is considered to be the center of a circle. Now when we say it is the region enclosed between two radius of the same circle, the region can be this one also. The region can be this one also. This is also the region enclosed between the two radius of the same circle. Then what about that feature? For that, we would be categorizing it basing on the angle. If you see at the center, we can say the total angle is 360 degree, and out of 360 degree, this sector is taking some part of the 360. Let that part be theta, an angle that it is taking as a part of 360 degree. Then the other angle, this angle would be 360 degree minus theta. If the value of theta is less than 180 degree, we consider it to be a minor sector. Minor means smaller sector. And if the theta is greater than 180 degree, we consider it to be a major sector. So here, just by observing the shape, we can say that this part is our minor sector. This part is minor sector. Then this part, this whole part, whose angle is greater than 180 degrees, this can be considered as a major sector. Major sector. Now, to find the area of that sector, we need to first of all observe the part of the circle a sector is taking. We know area of a circle is pi r square. In our previous session, we have done that area of the whole circle is pi r square. That means if the minor sector is taking a part of theta from the whole 360 degree, this area is for the whole angle, that is 360 degree, where there was no partition, where there were no sectors formed. It was a complete circle. That means the angle was 360 degree at the point O, that was at center O. But now, the angle at the center O has been divided into two parts. One is a minor angle, you can say, or you can say major angle if it's a bigger angle greater than 180. But simply we can say it has been divided into two different types of angles. We are moving on for the theta part. Presently let us do this one, minor sector. So this minor sector is taking theta degree, theta angle, a part of 360 degree. What part of 360 degree? This we have learned in our previous sections as fractions. A part of the whole, what we call it is a function. The whole was 360 degree. The part is theta. So this sector takes the part of the circle as theta upon 360 degree. This will be the part that the sector is taking from the whole circle. That means if the area of the circle is pi r square, then the area of the minor sector should be the area of that part which the sector is taking. And what part the sector is taking? The sector is taking the part theta by 360. So we can say area of minor sector is equals to the part of the circle it is taking, that is 3 by 360, into area of the circle, that is equals to pi r square. So this will be the area of the minor sector. Similarly, if you want to write the area of the major sector also, it's possible. We can write the area of the major sector is equals to the part taken by the major sector of the whole circle. And what is the part taken by the major sector? That is 360 minus theta whole upon 360. So you can write this way also, 360 minus theta upon 360. This is the part that the major sector is taking of the whole circle, and into the area of the circle, that is pi r square. So this would be my formula for finding the area of the major and minor sectors of a circle. Area of minor sector is theta by 316 pi r square, where theta is the angle of the sector. Area of major sector is 360 degree by 360 into pi r square, where 360 minus theta is the angle made by the major sector at the center. Now, that center, the angles are made at the center. So the angles are specifically termed as central angle. That means that theta can be considered as a central angle for minor sector, and 360 minus theta can be considered as a central angle for the major sector. Changing the values of theta, we can find the areas of different types of sectors as required in the question. Now, whenever we are saying sector, if we don't mention minor sector or major sector, whenever we say area of a sector, we mean that it is always the area of the minor sector only. You have to keep this in mind, that whenever we say area of sector, that means it is always area of minor sector and not the major sector. Now let's move to the segment of the circle. What is a segment? It is the region enclosed between the chord and arc of the circle. Between the chord and arc of the circle. Now, what is a chord? What is a chord? It is a line joining two endpoints of a circle. It can be any line. Say this is my chord. It is a line joining two endpoints of a circle. It can have, a circle can have infinite number of chords, and the longest chord is the diameter. This we have learned in our previous classes in class 9 also. Arc means it is the boundary of the circle. Segment is the region enclosed between the chord and the arc of a circle. If you observe this is my center of the circle, say O, this will be my chord, say AB, and the segment is the area enclosed between the chord and the arc of the circle. So this is the area that we are looking for. This part is called my segment. It is the region between the chord and the arc of the circle. So this is called segment of a circle. Similarly, moving as in sector, we have said, if it is the region enclosed between a chord and an arc, this is also the region that is enclosed between the chord and the arc. This region is also the region between a chord and the arc. That means if it is a smaller area, a small part of the circle, that means if it is not the diameter, if it is diameter, it will divide into two equal parts. So both the segments will have equal area. But here we see that this part, just by observation you can understand that this part is a smaller part of the circle and this part is the bigger part of the circle. Now this is the smaller part of the circle, that is why this one is called as minor segment. Minor segment of the circle. And this one, that will now become the major segment of the circle. If the chord would have been diameter, then the circle would have two equal segments. Since here we have taken the chord not as diameter, so we can very well show which part is the minor part or minor segment of the circle and which one is the major segment of the circle. Moving on to the next part, that is arc of a circle. What do we mean by arc of a circle? In the previous segment part also I have told you that the segment is a region enclosed between the chord and the arc of the circle. Then what was that arc of the circle? Let us know it very well. Let us draw a sector out here, two radiuses that would divide the total circle into two different sectors, minor sector and major sector, and then the angle enclosed by the minor sector with a theta, that is the central angle for the sector B, theta. Arc, if when we are saying that arc of the circle, it is the complete boundary. This complete boundary is the arc of the circle. Now, when two radiuses are going to form a sector, we see the total arc has again been divided into two parts. One is this part, this one, and the second one is this one. That is, the arc with the minor sector is my minor arc, and the arc with the major sector is my major arc. But before moving on to minor and major arc, what is the length of the arc? So we have learned in our previous sections also that length of the arc is circumference of the circle. The whole circumference or perimeter of the circle can be considered as the total length of the arc. Of that total length, when we want to find the length of the arc enclosed by the sector, the minor sector, that means we are talking about only this part, say AB arc. We want to know the length of the AB arc. AB is the arc that is along with the minor sector, that is making a central angle theta with the whole part of the circle. Then what is the length of the arc? AB. So length of arc AB. AB, now arc AB with central angle theta. This is my minor arc because it is a small part of the whole circle. And again we can say AB, the same terms AB, but now the AB is for the major arc, that means the angle for this arc will be 360 degree minus theta. So the part of the total arc that a minor arc takes is theta by 360 because the whole central angle at the center O, the total angle was 360 degree, and the minor arc is taking a part theta of the whole 360 degree. So the part taken by the minor arc of the whole arc is theta by 360. So length of the arc AB. Now if you want to make it more clear, so let us write it as length of the minor arc AB is the part taken by the minor arc, that is 360 degree, into circumference of the circle. And what was the circumference of the circle? The circumference of the circle is given by 2 pi This we have learned in our previous session also. This is the length of the minor arc, making an angle theta at the center is given by theta by 360 into 2 pi r. Similarly, we can also find the length of major arc AB. Major arc AB. So this will be the part of the arc taken by the angle made at the center by that arc. The part is 360 degree minus theta upon 360 degree. The total was 360 degree and the part that is taken is 360 by theta into circumference of the circle, that is again 2 pi r. Now let me tell you once again. Presently we are writing minor arc, major arc. Just remind that whenever we say length of the arc, we should understand it is the length of the minor arc. When we say area of the sector, that means it is minor sector. When we say area of the segment, we should understand that it is the area of a minor segment. Now we can conclude, or we have to remember some important formulas that we have discussed or we have gone through till now. Area of the circle, we have gone through in the previous exercise 12.1, there is pi r square. Circumference of the circle is 2 pi r. Area of the sector, we have discussed just now, theta by 360 to pi r square, and we should understand that area of sector means we are talking about area of minor section. Length of the arc enclosed by the sector, that means again we should understand that is the length of the arc enclosed by the minor sector is given by 360 into 2 pi r. But we haven't derived any of the formula related to area of segment of a circle. Then how do we find the area of a segment of a circle? Suppose we are given with a circle with center O, and there are two radii OA and OB which are making an angle theta at the center. And a chord AB is joined in order to obtain the segment ACB. Now, if you observe very clearly, the area of segment, this is my sector. From the sector, if you subtract the triangle, you get the area of the segment. So, very easily we can say that area of segment, we have to name the segment ACB is equals to area of sector OACB minus area of triangle AOB. Now area of the sector minus area of triangle is equals to area of the segment. Now in order to find the area of the segment, two important things we should know. One is area of the sector and the other is area of the triangle. Now area of the sector, we have a specific formula for finding the area of the sector. That is theta by 360 is pi r square. Then next is area of triangle. Triangle, which type of triangle it might have here? The type of triangle completely depends upon the central angle theta. If theta is 30 degree, the triangle is different. If theta is 60 degree, the triangle is different. Then how to find the area of that triangle? There are various ways to find the area of the triangle. But in class 10, we will be dealing with only those triangles with central angle 60 degree, 120 degree and 90 degree. Only three are considered in your syllabus in class 9. The central angle with 60 degree, the central angle with 90 degree and the central angle with 120 degree. So there are three different triangles and we should know what sort of triangles or how to find the area of the triangles when the central angle is 60 degree, central angle is 90 degree and central angle is 120 degree. So let us move on to this. When the central angle, number one, when central angle theta is 60 degree. That means, suppose this is a circle with center O and this angle is 60 degree, and if you join and make the chord AB. Now if you see, just observe the triangle AOB. If this is 60 degree, OA and OB are the radii of the circle. So they are same. That means according to isosceles triangle property, this both angles would be same, and by following the angle sum property of triangles, we will get this angle to be 60 degree and this also to be 60 degree, such that the sum of three angles in a triangle is 180 degree. So this will also be 60 degree and this will also be 60 degree. Now it becomes an equilateral triangle. 60 degrees, 60 degrees, 60 degrees. So it is an equilateral triangle. So when the central angle theta is 60 degree, the triangle formed is an equilateral triangle. And we know that area of equilateral triangle is root under 3 upon 4 sine square. Here you can consider any side because it's an equilateral triangle. Side can be OA, side can be OB, this is AB, all the three are same, and OA is the radius of the circle. So you can take R, and if you write to derive the area of the triangle for this part, you can write area of that equilateral triangle is root by 5 R square. This is the first condition. When the central angle is theta, you will have an equilateral triangle, and area of equilateral triangle is given by root 3 by 4 R square. The second condition, when the central angle is theta is 90 degree. So this is my triangle and the angle here is 90 degree. You make the chord, and this will be AB and O. And when this angle, the central angle theta is 90 degree, it's very clear that it is a right angle triangle with base R, height R, and hypotenuse AB. So here you can find the area of the triangle by the simple formula of finding area of any triangle, that is half into base into height, where base will also be R and height will also be R. So here it is a right angle triangle. This is right angle triangle. So area is equal to half into base into height, as compared to the triangle that we have taken. The base is equal to radius, the height is also equal to radius. So if you work right, this becomes half R square. The central angle theta is equal to 120 degree. When the central angle theta is 120 degree and AB is the chord that is drawn. Now it is an obtuse angle triangle. So let us draw a perpendicular from O on AB at C, such that we can find the area of the triangle by the formula half into base AB into height OC. In order to find the area, first of all we will have to calculate the value for AB and OC. Now as soon as we draw perpendicular from the center to the chord, it bisects the chord that we have learned in class 9. Perpendicular drawn from the center to the chord bisects the chord, that means AC is equals to BC. Now let us consider any triangle. In triangle OAC, a small triangle. Applying trigonometry, what we have studied in our previous class. If we apply trigonometry out here, let us consider that triangle this way. This is 60 degree. Say this one is my R, so this is R, O, A, C, and OC is the height of the triangle and AC is the base. We need to find two things. One is OC and second is AC. As soon as we get AC, we will multiply it by 2 to get AB. And that means the base of the triangle is obtained. And as soon as we get OC, we get the height for the triangle OAB. And then applying half into base into height, we can find the area of the triangle. We will be writing the formula for the area of the triangle. Now, while applying, this is my angle. So for this is my opposite part. For this is my adjacent part. And this is always hypotenuse, as we have learned in chapter 8 in trigonometry. So let us move on with sine 60 degree. Sine theta is opposite by hypotenuse. This we have learned in class in chapter 8 in our previous sessions. So sine 60 degree is opposite by hypotenuse. So we can write AC by OA. And the value of sine 60 degree is root 3 by 2. This also we have studied in chapter 8 trigonometry. This is root 3 by 2 is AC. We have AC and OA we have R. So we can write AC is equals to root 3 by 2 R. This we have got. As soon as we get AC, we can get AB. That is AB is 2 times of AC. So this is 2 into root 3R by 2, and this will be equals to root 3R. Then we need to find OA. In order to find OA that is adjacent to the given angle, we need to apply cos 60 degree, and that is equals to adjacent by opposite. Adjacent is OC and adjacent by hypotenuse, so OC upon OA. So cos 60, the value of cos 60 is half, 1 by 2. OC we need to find out, and OA we know it is R. So OC is equals to R by 2. So we have got OC is equals to R by 2. We got AC is equals to root 3 by 2R, and we have also calculated AB is equals to root 3. Now we will move on to find the area of triangle AOB. Right. Area of triangle AOB, and that is equal to half into base into height, and that is equal to half into, here we have base AB and height is OC. So we have base is AB and height is OC. So this is half into, we have obtained the value of AB as root 3R into OC also we have obtained as R by 2, and this becomes root 3 by 4R square. Almost the same as the formula that we have used for an equilateral triangle. We will have to show all these calculations in our sums also, or you can directly use the formula root 3 by 4R square also, as you wish. Both are permissible. Then let us discuss the example 2 from your NCERT textbook from chapter 12. Find the area of the sector of a circle. Find the area of the sector of a circle with radius 4 cm and of angle 30 degree. Here the angle 30 degree means central line. Also find the area of the corresponding major sector. That means we need to find the area of the minor sector also with central angle 30 degree, and area of the corresponding major sector also. That means we are given with a circle with central angle 30 degree. A sector is drawn, and the angle central angle of the sector is 30 degree at the center, and the radius of the circle is given as 4 cm. We need to find the area of, let us name it O, A, B, let us write here C and here D, so that we can very easily name the major and minor sectors. We need to find the area of the sector OACB. Moreover, we need to find the area of the sector OABB. We have to find the area of both the sectors. So let us continue with finding the area of minor sector. That is area of sector. As I have told you earlier, whenever we write sector, it means minor sector. So area of sector was given by the formula theta by 360 into pi r square. And here the theta is the central angle that is given to us as 30 degree. Substituting, this is 30 by 360. We have to take the value of pi as 3.14 into r square, that is radius is 4 into 4. Cancel it and separate. 12 and 4 3s. So this is 12.56 by 3, which is 4.15. Sorry. 4.18 approximately centimeters. So this is the area of the minor sector. Now in order to find the major area of the major sector, we have two methods. Either you can find directly with the formula that I had given you in the previous part, that area of the major sector is 360 minus theta by 360 into pi square. That is one way of finding. The second way of finding is you can find the area of the whole circle and subtract the minor sector from it. Then also you can get the area of the major sector. We will do it in one method. So area of major sector. What was the name of the major sector? That is OABP. We will be using the formulas 360 minus theta by 360 into pi r square, where theta is equals to 30 degree that we have seen. So this is substituting 360 minus theta upon 360, and the theta value is 30 degree. Into pi we have to take 3.14, and the radius is 4 into 4. This is 330 upon 360 into 3.14 into 4 into 4, and let us simplify it. 0 cancels. 3 11s are, 3 12s are, and 4 3s. So we have 11 into 3.14 into 4 by 3. This part we have sorted out there also. The value we got is 4.14 approximately. So this is 11 into 4.18. This will also be an approximate value in terms of centimeters square. If you solve it, this is 8, 11, 11, and 8, 19. 144 and 145.98 centimeters square approximately. Let me check out once again. It is 45.98 approximately, that is correct. Moving on to the next example, example number 3 from the NCERT textbook. The question is, find the area of the segment A by B as shown in figure 12.9. This is figure 12.9 that is given in the textbook. If the radius of the circle is 21 centimeter, the radius of the circle given to you is as 21 centimeter, and angle AOB is equals to 120 degree. Angle AOB is 120 degree. We need to find the area of the segment A by B. That means we need to find the area of this part. This we have discussed this type of example that we have seen by deriving the angle when the central angle was 120 degree. This is the same as that one, so we will have to move accordingly. Let us take the triangle first. And we know that area of the segment is area of the sector minus area of the triangle. That also I have told you earlier. So let us take the triangle first. Let us take the triangle. The radius 21 centimeter. This is also 21 centimeter. Central angle was 120 degree. And if you draw perpendicular from the center to the chord, it bisects the chord. That means this part is equal to this part. This is A, B, let us name it as C, and this is O. And the central angle is also bisected into two equal parts. So you can say this is 60 degree, and this is also 60. So we need to find the area of the triangle. Then we need to find the area of the sector. Then we will be subtracting the area of the triangle from the area of the sector to get the area of the segment. So let us consider a small part of it. In triangle AOC, this triangle, for this triangle, this this is my angle, so this is adjacent, AC is opposite, and OA is the hypotenuse. So we will be writing sine 60 degree. Sine 60 degree means opposite by hypotenuse. Sine 60 degree means opposite is AC by hypotenuse is OA. So sine 60 the value is root 3 by 2. AC we are looking for, and OA is 21 centimeter. Why we are looking for AC? Because in order to find the area of this triangle, we have to use the basic formula half into base into height, and this is the perpendicular that was drawn. So for this triangle, the base is AB and the height is OC. As soon as we get AB and OC, we can get the area of the triangle. That is why we are looking for AC. So AC is equals to 21 root 3 by 2 centimeters. Now AB is the double of AC because AC is equals to BC. Which we have done that perpendicular drawn from the center to the chord. Bisect the chord, so 2 equal halves are there. AC is equals to BC. So AB can be twice of AC. So we can find AB is equals to twice AC. So this is 2 into 21 root 3 by 2, and this can be written as 21 root 3 centimeters. So we have got AB. Now we need OC, which is an adjacent as per our triangle. So we have to take cos. Cos 60 degree is adjacent, that means OC upon hypotenuse, that is OA. And cos 60 the value is 1 by 2. OC we are looking for, and OA is 20. So OC is equals to 21 by 2 centimeters. Now we have got the base for the triangle also, the height for the triangle also, and we can find the area of triangle. So area of triangle AOB is half into base, that is AB, into height, that is OC. So this is half into AB we have got as 21 root 3, 21 root 3, and OC we have got as 21 by 2, so this is root under 3 by 4, 441 centimeter square. Keep as it is. If you want to solve it, you can solve by substituting the value of root 3, but it is not given in the question, so we will not solve it. We have got the area of the triangle. Now we need to find the area of the sector. So area of sector. This sector name is OAYB. OAYB. And the area for the sector means it is always considered to be the minor sector. That is theta by 360 into pi r square. So theta is 120 for the sector. This is 360 pi 22 by 7. We are asked to take in the question, and radius is 21. So this is 21 into 21. 3 7 7 as this is 21 into 22. So this is 21 2s are 42, 2 carry over 4, and 462 centimeter. So now we have got the area of the sector also, we have got area of the triangle also. We just need to find the area of the sector. Now the area of the segment AYB is equals to area of sector OAYB minus area of triangle AOB. We just need to substitute and get that answer. This is 462, the area of the sector, minus root 3 by 4, 441 centimeters. So this is the final answer that we are getting. That area of the segment is area of the sector minus area of the triangle. Area of the triangle we have got, area of the sector we calculated, and just substituting and solving, we got the area of the segment to be 460 minus root 3 by 4, 441 centimeters.